I'm sure that you know what a camera sensor is, and you probably know the different sizes and how they affect zoom range. However, there are things you might not know how sensor sizes affect, like dynamic range or ISO performance, and even if you do, you might not know why. So today, I'm breaking down everything there is to know about camera sensors. Well, at least from a photographer's point of view. I'm not talking about making them. Anyway, let's just get to the video. Hello, I'm Noah from Anything Cameras, the channel that focuses on helping you improve your filming and photography. And today we're telling you just about everything there is to know about camera sensors. To fully understand everything about camera sensors, we need to start at the very beginning. And by the very beginning, I mean, what is a pixel? Now you might be saying to me or to yourself, well, I know what a pixel is. It's a little tiny square of color inside of an image. Well, I would say you're right, but only to an extent. Because, have you ever thought about how a camera captures pixels? A camera sensor is way more complicated than you might think. It's actually a grid containing millions of little squares where the sensor can capture electrons, and those little squares are pixels. And on a sensor, pixels are like pails or buckets for collecting light information, those electrons. And based on how many electrons and what those electrons are like, the sensor can tell the camera, or rather the processor, what the brightness of the pixel is, what the color is, a whole bunch of different stuff. Now, how that grid on the sensor captures electrons and processes them gets really complicated, and I don't even understand it myself. But a good place to start about learning how sensors interpret and capture light would be bit depth and color depth, which we'll be talking about later. Now, why knowing what a pixel is important for understanding things like megapixels and why full frame reduces digital noise. I'm getting to that still, but I still need to explain sensor size. And don't worry, it's a lot more simple than that whole crazy grid containing pixels and capturing electrons. Well, actually you might want to worry because after sensor sizes and megapixels, it gets geeky. So the sensor size is easy. It's how big your sensor is. And you probably know different sensor sizes like Micro Four Thirds, APS-C, full frame, APS-H, Canon APS-C. There are a whole bunch of different ones. But for this video, we'll be focusing mostly on APS-C and full frame. But the math we use can apply to any sensor size as long as you know its crop factor. Now onto megapixels. When I say that a sensor has a grid containing millions of pixels on it, I mean it, because a megapixel is how many million pixels are in that image. So if you have a 24 megapixel image, that image in a standard 3:2 aspect ratio is 6,000 pixels wide, 4,000 pixels high. And to get the area of a square, you multiply the width by the length, which in this case is 6,000 times 4,000, multiply those together, and you get 24 million, hence 24 megapixels. Megapixels and sensor size is where we get sensor pixel area from. Now, sensor pixel area is used when you're talking about things like digital noise level between two sensors, and really what it is the ratio of the size of pixels on one sensor to another. These sensors can be different sizes. The pixels are obviously different sizes most of the time, and we'll be getting into that later. But to calculate the sensor pixel area, we need to calculate the size of a pixel on a sensor. The size of a pixel is determined by how many megapixels you have. Because if you think about it, you can have, say, an 8 megapixel full frame camera, so the sensor is nice and big, and that only has 8 megapixels, meaning the pixels themselves can be much larger to take up all the surface area. But then you can have a 30 megapixel APS-C camera. That's a smaller sensor and more megapixels, meaning that to fit those pixels onto that sensor, the pixels themselves need to be much smaller. That means that an 8 megapixel full frame camera, which is super low resolution, only needs to fit 3,264 pixels across it. But if you have a 24 megapixel APS-C camera, that has to fit almost twice that many at 6,000 pixels all the way across it. So before we calculate the size of a pixel, just keep in mind it will be a rough estimate, because on a sensor you can actually have gaps in between individual pixels, meaning that it won't be exact. Okay, now, To calculate the size of a pixel on a 24 megapixel full frame sensor, it's like this. The width of the sensor in millimeters divided by the number of pixels it fits across. Yep, it's that easy. Width divided by pixels, W/P. That easy. So, you may know that a full frame sensor is 36 millimeters across. Like I said, a 24 megapixel image is 6,000 pixels across in a standard 3:2 aspect ratio. So we divide 36 by 6,000 and we get 0.006 millimeters. Now this is not the area of the pixel. This is the width of a pixel. So to get the height for the pixel, to calculate the area, we can do the same equation with height, or just skip all that math because a pixel is a square, so the width is the same as the height. So to get the area of a pixel, we multiply 0.006 millimeters times 0.006 millimeters, and that comes out to be 0.036 millimeters. The pixel pitch, which is the term used for the width of a pixel on a full frame 24 megapixel camera, is going to be approximately 0.006 millimeters, and the area of the pixel is going to be 0.036 millimeters. But you need to note that they're not usually expressed in millimeters. Usually it's microns, and a micron is 1/1000th of a millimeter. So if we go back to the pixel pitch of the 24 megapixel full frame sensor, that is 0.006 millimeters. The 6 is in the thousandths place for the millimeters, meaning that it is 6 microns. There we go. So the width of the pixel on a 24 megapixel full frame sensor is 6 microns, and that just reduces a bunch of zeros since you're working with millimeters otherwise. So yeah, a lot easier. And by the way, a micron symbol is the Greek letter mu followed by a lowercase m, so it looks like this. Okay, now we're on to crop factor. A short rest from Super Geeky. Now, chances are you know what crop factor is, how it relates to zoom ranges, and definitely what crop factor your camera has. But do you know why there's a crop factor in the first place? Or what determines the crop factor? Because that's what we're going to be talking about mostly. So, just for those who don't know what a crop factor is, to start, let's go back to good old APS-C. APS-C has a 1.5 times crop factor. Or if you're on Canon, 1.6, but we're using normal APS-C, so 1.5. A full frame camera has a crop factor of 1, because that's a standard. And so you multiply your zoom range by 1 on a full frame, you get the same zoom range. So yeah, you don't need to do anything with full frame. Also, don't forget that this math works with any sensor size's crop factor, so if you have a Micro Four Thirds camera or an APS-C H camera or a medium format camera, you can follow along with us. Now, the math for how a crop factor affects zoom and aperture is super easy, but you need to note you only apply the crop factor to the aperture if you are trying to calculate the depth of field. It does not affect exposure. An exposure of 1/100th of a second, f2.8, ISO 100 on a full frame is going to be the same exposure on an APS-C. The crop factor with an aperture only affects the depth of field, the background blur in the image. Okay, now with that disclaimer out of the way, we can go and do the math. Hopefully that makes sense, but if not, just ignore the aperture in the following math. Now, for calculating the full frame equivalent value of a crop sensor is easy. Multiply the values by the crop factor, so in this case 1.5. So if we have 50 millimeters f2.8 on an APS-C, we multiply those out by 1.5 since we're working with APS-C, and it turns out to be 75 millimeters f4.2 full frame equivalent. But remember, that aperture only affects the background blur, not the exposure. That is the full frame equivalent of 50 millimeters f2.8 on an APS-C. Hopefully that made sense. If not, let's say you wanted an image that had the same zoom and depth of field as a full frame 50 millimeter f2.8. On an APS-C, you divide those numbers by 1.5. So that comes out to be 3.33333333333, etc. millimeters f 1.8666666, etc. And you would have to make the shutter speed faster or the ISO lower to get a darker image, since opening up that aperture changes the exposure, but remains the same depth of field. I really hope that all made sense. I know I say it a lot, but it can get very confusing. So to understand why there's a crop factor, let's start with what determines a crop factor. To do this, let's look at the size of an APS-C and a full frame sensor. A full frame sensor is 36 by 24 millimeters. An APS-C varies, but is generally 22.2 by 14.8 millimeters. If we calculate the diagonal of these sensors using the standard equation, the Pythagorean theorem, d equals the square root of w to the second power plus l to the second power, where d is the diagonal, w is the width, l is the length, then doing the math, d equals the square root of etc. becomes d equals the square root of 22 to the second power plus 14.8 to the second power for APS-C, and blah 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 squared to the 2, blah blah blah. You get the rest. So in the end, the full frame diagonal is 43.27 millimeters, and the APS-C diagonal is 26.68 millimeters. Dividing the full frame diagonal by the APS-C diagonal, we get roughly 1.5087166688, hence the 1.5. The same equation works with any sensor size. Also, the reason we use a diagonal is because the lens projects a circle of light, and we want to, for the most exact equation, so to do this, we need to use the diagonal of the sensor, since that cuts through the middle, whereas the width and the height only go through a portion of it, since they're closer to the top and bottom. So if we calculated this out using the width or the height, we would get the same answer for both, which is 1.621621621621621. You get the idea. It's a never-ending decimal. So, why is there a crop factor in the first place? The reason why crop factor exists is because of when you put a full-frame lens on an APS-C camera. The sensor is much smaller than that image circle, so the diagonal of the sensor does not take up the full width of the circle like a full-frame sensor on a full-frame image circle would. So that means that the APS-C sensor only sees the middle portion of that image circle, meaning that it's cropped, hence the name crop factor. If this is hard to understand, try picturing an APS-C lens on a full-frame sensor. An APS-C lens is designed for APS-C so that the sensor takes up the whole width of the image circle. However, a crop factor still applies here because of full-frame lenses on an APS-C sensor. Anyway, now take that APS-C image circle and in your mind, put it on a full-frame sensor. The sensor is much bigger than the circle. In fact, you don't have to imagine that. We can put it on screen for you here. But also it exists because of aperture. If you think about it, the exposure between different cameras and sensor sizes needs to stay the same, but the depth of field is affected, so hopefully that makes sense. It's kind of hard to put into words. Yay, on to ISO! We're about to find out why sensor size affects digital noise. So you will always hear that a full-frame sensor works better in low light than an APS-C sensor, and this is true for a very good reason. Remember the sensor pixel area and how we calculated the size of a pixel? Well, to give you an idea about why megapixels and sensor size affect digital noise, let's go back to pixel size. You should remember we compared the size of pixels on a 24 megapixel full frame camera to the size of a pixel on a 24 megapixel APS-C camera. To fit all those pixels across the APS-C camera versus the full frame, those pixels had to be smaller. So with that in mind, think about the amount of light hitting those pixels. Since the pixels are smaller on the APS-C camera, they can't gather as much light as the pixels on a full frame camera. So a bigger pixel captures more light. Is this making sense yet? So this is one place where sensor pixel area comes in. If you remember, the sensor pixel area is the ratio of the size of a pixel on one sensor to another. But we never ended up calculating that, so let's calculate that. It's actually very easy. Let's go back to microns. We already know that 24 megapixels on a full frame camera has a pixel pitch of 6 microns and an area of 36 microns. If we do that same equation for APS-C, we get 22.2 divided by 6,000. That comes out to be 0.0037 millimeters, or 3.7 microns. For the ratio of a pixel to another across the two theoretical cameras, we just square the pixel pitch to get the area of the pixels and calculate the difference. Now, we need to calculate the area of a pixel on an APS-C camera. So we already know that the pitch is 3.7 microns. We square that, which is 13.65 microns. Now we have the area of the pixels, 36 microns and 13.65 microns, and we need to calculate the difference. To calculate it, we need to subtract the APS-C number from the full frame number, so 36 minus 13.65 comes out to 22.35. We divide that number by the original full frame pixel area, which is 36. So 36 divided by 13.65 comes out to be 1.63736264, or rounding 1.64, which means that the full frame pixel is 164% bigger than the APS-C pixel. Does this mean that the full frame sensor is going to perform 164% better in low light? Yes and no. The pixel size is not the only variable when it comes to digital noise. The processor, the settings, the scenario, and other variables produce different results. But if you had the exact same camera, whose only difference was the size and sensor, in the same scenario with the same settings, then theoretically, yes, the full frame would perform 164% better, but there's not really a good way to measure the performance of one camera in digital noise to another, so the percent there doesn't even matter. It just gives you a rough idea. So with this in mind, just keep in mind that that does not mean that an 8 megapixel full frame camera from 2006 will perform better than a 30 megapixel APS-C camera from, say, last year, because the processor plays a big part in how much digital noise in an image there is, and that technology has progressed so quickly that megapixels just don't keep up with it. Now, as we get on to dynamic range, we need to talk about signal to noise ratio, N/N. If you have a low SN, then you get more noise. In a high signal to noise ratio, you get less noise. Now, the signal here is referring to the amount of light hitting the pixel or the sensor. The higher the signal, the brighter the image is. The lower the signal, the darker the image or pixel is. This SN ratio is why when you try to recover shadows, not only does it lose detail, but it gets super noisy. But when you try to recover highlights, while there might not be much detail there, there's no noise. This also goes back to ISO performance. When you have a bigger pixel, there's more light hitting that sensor, meaning a higher signal, less noise. We're now on to dynamic range itself. Dynamic range is defined as the range or difference between the strongest signal and the weakest, captured by an image sensor in a single photo. Now, remembering that the strong signal is bright and the weak signal is dark, these are undistorted signals, meaning that they're not clipped, they still have detail in them. Clipped means that there's just no detail in them, the shadows are way too dark and the highlights are way too bright. That also means there's no color in them because it's just all white or all black. The larger the dynamic range, the larger the range of tonal values and colors a camera can capture and display. For example, a camera with high dynamic range could capture something really bright, but still have details in the shadows. A larger sensor, combined with larger pixels, can provide more dynamic range with less noise. However, just like with the digital noise, the processor in the camera plays a big part as well, and the settings and the scenario, everything. Now, the aperture and the shutter speed affect how much light actually hits the sensor. The ISO determines the amplification of the signal. Therefore, the higher the amplitude, the more noise there is. This means that higher ISO values equals less seen light, the light captured by pixels due to shutter speed and aperture, smaller SN ratio, smaller dynamic range, more image noise. A lower ISO value means that more light is hitting that sensor, since you had to increase the aperture and shutter speed for more light to get the same exposure. And that means that there's going to be a higher SN ratio, meaning larger dynamic range and less image noise. This means that no matter the camera or the sensor, higher ISO means more noise and less dynamic range in the final file. Also regarding sensors and image quality are color depth and bit depth. We already made a video about chroma subsampling and bit depth, but I do need to make a very, very slight correction to that video. In fact, it's not even a correction. All of that information in that video is correct. We just got a term slightly wrong, but I'll explain why they are mostly interchangeable. What we were referring to as bit depth really should have been referred to as color depth, but like I said, the terms are very interchangeable because of how a camera sensor works. So I'm about to explain that. After the exposure of a camera, the signal is taken by the pixels and processed and converted to binary code, which you may know as the computer language containing only ones and zeros. These ones and zeros are called bits, and these bits are what make up the shades of black and white. So if you have a 1-bit image, that means there are only two possibilities, 1 or 0, black or white. A 2-bit system can have 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And that would be something like white, light gray, dark gray, black. A 3-bit image has 8 different combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. So the bits are shades of black and white that the camera can capture. An 8-bit image has 256 shades from black to white that it can capture. And this number may sound familiar if you watched our chroma subsampling video, because an 8-bit video has 256 shades of red, green, and blue. How you know how many different combinations a different bit image has is you multiply 2, since there are only ones and zeros, to the power of the number of bits. So a 2-bit system would be 2 to the for the ones and zeros to the power of 2 for the number of bits, which comes out to be 4. And if you remember, the 2-bit system has 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. So if you have a 4-bit system, you multiply 2 to the power of 4, and that comes out to be 16. So 2 to the power of 8 for an 8-bit system comes out to be 256. And a 14-bit photo, which is not uncommon in RAW files, has 16,384 shades of black to white that the image can capture. Now this is where I explain why what we were referring to as bit depth in that chroma subsampling video was actually color depth, but why it's not misinformation at the same time. Because bit depth is the luminance level of white to black, or the levels of light, but those shades of white and black are interpreted into color by the Bayer filter, because those levels of light have different color. The Bayer filter is a filter over the sensor that interprets color. You may already know what this is, and you may even know that there's a difference between Fujifilm Bayer filters and Canon Bayer filters. But I'm not going to be getting into that today because this video is already long enough, right? So the Bayer filter can only interpret the 3 primary colors when it comes to digital colors, which are red, green, and blue. Which is why it's important that you have a lot of shades of each of those colors, because without a lot of shades of each of those colors, you can't have colors like purple or yellow. And even though the Bayer filter can only interpret these 3 colors, they can interpret any shade of these colors. Hence what I just said. So if you have a 1-bit sensor with a Bayer filter over it, then there's not going to be any color, because a 1-bit system only has 2 options, 0 or 1, white or black. And white and black don't have any color. Therefore, no color. However, if you have an 8-bit system, the sensor can capture 256 shades of white to black, which the Bayer filter interprets the color on, so the limiting factor is the sensor, not the Bayer filter. Hopefully this is making sense. Thus, the bit depth and the color depth of a sensor are the exact same, which is why the information in the chroma subsampling video is not incorrect. It was just a slightly incorrect terminology. How the Bayer filter works is that it's a filter over each individual pixel individually, which means that one pixel can only see one color. So the Bayer filter is laid out with 50% green, 25% red, and 25% blue pixels. Or typically, Fujifilm and other companies do it slightly differently. Usually the percentages remain very similar though. The reason why they're twice the amount of green pixels is because the eye perceives green as 200% brighter. Hence there being twice as many green pixels. So red light passes through the red pixels, while green light and the blue light do not pass through the red pixels, and the blue light passes through the blue pixels while the red and the green light don't pass through the blue pixels. You get the idea. Each pixel can only collect the primary color of information it's assigned to, red, green, or blue, along with the number of electrons collected in the pixel well, which determines the tonal value or the brightness of the pixel, using bit depth. Using all this information and a series of algorithms and interpolations, the processor can interpret this data into a final image. The precision and accuracy which this information is communicated and displayed in the final image is determined by the bit depth, and that's why bit depth and color depth are pretty much interchangeable. The Bayer filter can interpret any level of light of those three colors. It's the sensor and the bit depth that's the limiting factor. And that's also why you can still have black or white, because black is the lack of color, white is a lot of color, basically. I hope everything made sense. Please subscribe and comment if you want more nerdy videos like this. I'm Noah. Thanks for watching. And we need to calculate the... calculate.